Alright, so another derivative for acids, for carboxylic acids, is acyl halides. Acyl halides. So this is the acyl group with a halide. Let's say the halide is a chlorine. That's the most common one. So this functional group is gonna be called acyl chloride. Okay, that's an acyl chloride. It's gonna be more reactive than the acids and the esters. Remember, that's the carboxylic acid and that's the ester. And in fact, if it's more reactive than these two, then it's definitely more reactive than the least reactive, which is the amide. It's definitely more reactive than the mixed ester. We call it an anhydride. So this is, whenever we do acyl substitution reactions, this is the guy we like to use, because chlorine is a good leaving group. The nucleophile attacks, okay, the chloride falls off, and you can end up with your nucleophile substituting the chloride after the nucleophile attacks the carbonyl of the acyl halide. So they're usually man-made. We make them to use them. They don't exist in nature, obviously, because the chlorine is a very good leaving group. For example, in nature, most of the time, for example, in the cell, you have too much water. So if you have too much water, guess what will happen? The Cl will definitely be replaced by the OH. Again, I'm showing you the shortcut here because you're going to lose HCl as you do the condensation reaction. You get hydrolysis. For example, if you have water. Same thing happens if you have an alcohol. You can convert the acyl chloride to an ester. If you have an alcohol, you're still going to lose HCl. So alcohols and waters and amines are always gonna kill your acyl halide. So it's usually not found in nature because it readily undergoes such substitution reactions. Like I said, it's chlorine that's the most common. It's very, very rare for you to find a bromide and iodide being used in organic chemistry. We like chlorine. So how do we make them? They're prepared by using what we call thionyl chloride. Okay, that's a thionyl chloride that's used to replace the OH with a Cl. Or you can use phosphorus pentachloride. This again is just a source of Cl. Just like thionyl chloride is a source of Cl, you replace the OH with a Cl. In turn, you're gonna lose HCl. You lose sulfur dioxide from thionyl chloride. You lose HCl still, and you lose phosphoryl chloride. Okay, this is called phosphoryl chloride. So you don't need to worry much about this in the test, but you should know generally that if you start with a carboxylic acid, you're adding thionyl chloride or phosphorus pentachloride. All you're doing is switching the OH with the Cl. That's why this is a nucleophilic, like we stated when we started in yesterday's lecture. This is a nucleophilic substitution reaction. It's not an addition, it's a substitution because the OH is replaced with a chloride using either of these two reagents. Okay, so same thing will happen if you use alcohols. I gave you the shortcut. You'll always lose the H of the alcohol and the Cl. That's how you get HCl, and then the rest of the alcohol clicks onto the carbonyl, which is this, because here you have 2 hydrogens. I know that because carbon should have 4 bonds. Here you have 3 hydrogens. I know because carbon should have 4 bonds. So it's 3 hydrogens and 1 other bond. Okay, so that's the OAT part because that's an ethyl. So that's a substitution. This is a better way to make esters. No catalyst is needed because Cl is a very good leaving group, and in fact there's no equilibrium. It's one way. Remember how we made esters before? An R group with a carboxylic acid is reacted with an alcohol in presence of an acid catalyst, right? So that's how we made our ester in the last class. Okay, that part. So you have C and C, that's an ester. So this reaction was called, right here, this was called Fischer esterification. That was Fischer esterification. The problem with this reaction, we said, is it goes back and forth because it's acid catalyzed. But if you use this method with azo halide, you don't need an acid catalyst. So no catalyst needed. See, nothing is put onto the arrow here. Only the temperature indicated. And there's no equilibrium. Only one going forward arrow that's used. And the main reason is because Cl is a very, very excellent leaving group. So HCl is normally released. That's why one in the lab has to do this reaction in the fume hood, because if you inhale HCl, it goes into your respiratory tract and reacts with a delicate covering of your lungs, and before you know it, you start coughing blood. So such a reaction has a limitation because the HCl released is gonna kill you as fumes. But here, whenever you do Fischer esterification, the only byproduct is H2O. Obviously, H2O won't kill you, and it's not fumarous. But HCl is gonna come out as fumes. So you have to use the fume hood. In fact, all organic chemistry reactions must be done in a fume hood for safety. They are very, very, very unpredictable. So mechanistically, if you want to do esterification by method of using an alcohol and Si halide, the mechanism is like this. So you see, we don't have an acid catalyst. This time I don't need to use this oxygen to accept a proton. So use your lone pair, attack the carbonyl of the acyl halide. Okay, that's your acyl halide, and this is your alcohol. Okay, it's an alcohol because you have HOR. So attack the carbonyl of the acyl halide. Remember, we are attacking because this is partially positive, the oxygen is partially negative because of the lone pairs, and then the pi bond opens up, giving the two electrons that made the pi bond to the other oxygen. So you started off with an sp2 carbon center, you're ending up with an sp3 carbon center, and this happens to be tetrahedral intermediate. Now, because it's a tetrahedral intermediate, we need to go back to our sp2 center to make a carbonyl. So you use one of the lone pairs on oxygen, okay, to remake the carbonyl as the Cl falls off because it's a good leaving group. So Cl fell off, it's a good leaving group. Okay. Now, remember when the alcohol attacked, it's still holding on its proton. Okay, still holding on its proton. So we have to use the leaving group that left to come back and deprotonate it, because I always tell you the molecules always like to be neutral. Organic molecules like to be neutral, and that's how you get your ester. And because the Cl took out the hydrogen by proton transfer, you get HCl. And that's the HCl I kept on telling you that you can use this shortcut right here, project, expose your hydrogen of the alcohol, lose it with the Cl, you lose HCl, but the mechanism has clearly shown you where the HCl comes from. So you will have converted your acyl halide to an ester to an ester, your alcohol that you used is ethanol or ethanol. Byproduct is HCl. That's your ester product. So the reaction is still esterification, but using just the acyl halide as an alternate route. Like I said, acyl halides are very sensitive to water, so water can be used to break down hydrolysis. Lysis break down hydro water. So you can break down the acyl halide by help of water. Again, like I said, you can use the same shortcut. HNCl is lost. You get that product. So the OH that's left clicks onto the carbonyl. You get the carboxylic acid. So this is why you really want to make sure you make this acyl halide and use it the same day. If you let it sit around, especially in Louisiana where it's humid, it's just going to react with the moisture in the air and revert back to the carboxylic acid. You lose it. Okay, they're very reactive. Very reactive because again the Cl is a good leaving group. So that will be the hydrolysis of acyl halides back to their carboxylic acid parent molecule. The same acyl halide functionality can be broken down using ammonia, so we call that ammonolysis. Lysis is breakdown using ammonia to produce an amide. This reaction can be used to make amide bonds. That's the amide bond. It says two equivalents. The reason being, you'll see it. Okay, the mechanism is not there. I'm gonna draft it. So the first equivalent can be used to make this compound right here. If you use your shortcut, you can just show one molecule of this and then lose HCl. You should have lost HCl, but because we have two equivalents, the second equivalent will react with HCl. Okay, so this equivalent would have reacted with HCl to give you this. But let me quickly draft for you the official mechanism. So first equivalent, this is just the shortcut of predicting how you can make the product, because the NH2 will just click to the carbonyl, but I'm going to show you the extended mechanism. So you attack the carbonyl, that opens up. Here you get O minus, Cl is still there, ammonia is still there, but the nitrogen get a plus charge. This oxygen uses its lone pair to make a carbonyl as the Cl leaves. So you get this molecule. Okay, that's the carbonyl, and I'm just gonna write it as NH2 with the hydrogen on there plus the Cl left. Then the Cl comes back to take out this hydrogen that is neutralized. That's how you get this product. You're gonna get HCl and ammonia. Alternatively, instead of using Cl minus to take out the hydrogen, you use the second equivalent of ammonia. You see how there are two of them here? So one can be used to, sorry, this is NH3. One can be used to attack. The second equivalent can be used to deprotonate. And in which case, you're gonna get NH4 plus when this deprotonates. But because you lost Cl minus here, the Cl minus will be there. So there are two ways you can show your byproducts, but for me, the main principle is that you get this. That's the main key point. You can quickly just, because I won't ask you to draw the mechanism in the test, I want you to know how to use your shortcut. Expose one of the hydrogens, lose HCl. The main product will be this, the main organic product. So two equivalents are needed. One is, the first equivalent is going to be used to make the amide, which is that. The other neutralizes the HCl. So use the ammonia, take the hydrogen, the ammonium formed will neutralize the Cl. Alternatively, if HCl and ammonia are existing together, Both of those will give you ammonium chloride, whichever way. SA halides are also used in Friedel-Crafts acylation reactions. I think we talked about that in chapter 4. If you've forgotten, let me show you. So let's say you start with a benzene and you add an SO chloride. The catalyst of choice is usually AlCl3 for Friedel-Crafts acylation. Again, you're just losing that and clicking the rest of the structure in the ring. So let's say this was our hydrogen. That hydrogen is going to be replaced by the SO group. Okay, so whatever this R group is going to be put there, and then you're going to lose the Cl. Actually, you're losing HCl because this hydrogen will be taken out. The Cl fell off, you make HCl. So again, you get a ketone in that case on the aromatic ring, and that's the Friedel-Crafts acylation reaction, and you used the SO chloride for that purpose. So another more reactive form is the anhydride. Okay, there are acid derivatives. If you start with OH, replace the OH with what looks like a carboxylate. Okay, so this part replaces the OH. That's an anhydride. So how do you make it? You use 2 equivalents of carboxylic acid. It's a condensation reaction. Let me show you the shortcut again. So one will play the role of an electrophile. The other acid will play the role of a nucleophile. Okay. So you still, okay, so let's say this loses the hydrogen, the other one loses the OH. So eventually you're gonna lose water. Okay. You're gonna lose water. I'm gonna complete the drawing. I don't want to keep switching pens. Let me complete the drawing, then explain again. Okay, yep. So this part clicks to the rest of the black part. You get your anhydride. Notice that this whole group is an R group. This whole group is an R group. That's why anhydrides will have R groups on both sides with a carbonyl separated by an oxygen. So water is lost. Again, I've given you the shortcut so you don't stress yourself on the mechanism. That's not the main principle, main target for this class. Okay, so we always use high temp for this reaction. So if you use the high temp, it's gonna help to vaporize off the water according to what we call Le Chatelier's principle. If the water is taken out, the reaction is forced to go forward because there's more space this way, so you keep making more products. Okay, applying Le Chatelier's principle, which states that if a system is subjected to a stress, the system counteracts to fight back the stress to gain equilibrium. So the reaction will keep moving forward because with high temperature, you can imagine water will be driven away. To avoid high temperature, we usually use the acyl chloride to make anhydrides. Let me show you what happens mechanistically. For example, using this example, I already gave you the shortcut to get a feel of of what happens if you have 2 equivalents of the carboxylic acid. Like I said, one will play the role of an electrophile, the other will play the role of a nucleophile. So this portion is playing the role of nucleophile. This portion is playing the role of electrophile because it's attacked by the other one, by the partner. So you use the oxygen to attack the carbonyl. It's partial positive, that's why it's attacked. Pi bond opens up. You end up with an sp3 intermediate. I'll keep telling you that this tetrahedral intermediate is very important for these reactions on this chapter. Okay, So you started with sp2 carbon center, now you have sp3 carbon center. So this oxygen comes down and then the OH leaves, you get what looks like an anhydride, but because OH that left is a good leaving group, you'll expect that this will be taken out, that will be neutralized. You end up with your anhydride. So whatever arrows I've drawn here are just simply these arrows again, because this plays the role of a base to do the proton transfer deprotonation process. You end up with your anhydride. Now notice that the OH takes out hydrogen, you get water, and that's the water that's lost because we have high temp being used for this reaction. So please use this shortcut I showed you. One will lose the H, one will lose, the other one will lose the OH. Click whatever is outside the circled circle or circled area. Click them together, you get your product, which happens to be an anhydride. Water is lost. Of course, the black hydrogen is lost. The red OH is lost. Alright, so what if the two, you see here, the carboxylic acids are separate, right? So what if they're on the same ring, on the same structure? So it's the same process. 1, 2, 3, 4, and 5. So you're gonna make a 6-membered ring with 5 carbons on it. Okay. So in fact, if I use a black pen, where this will be the black part, so that keeps its oxygen, but the other one is gonna lose its OH. So this loses OH, this loses hydrogen. Click it together, you get your cyclic anhydride. Okay, and of course you're losing water. So alternatively, you can use SO halides. Instead of using a carboxylic acid, you use a carboxylate, which is a beta nucleophile. If this attacks the carbonyl and oxygen opens up, see if there's a mechanism that's done. So you'll get a tetrahedral intermediate, of course, and the other part comes with its carbons. So I'm using this as the black part, which is this part that attacked, the oxygen that attacked is the black one, which is this. Pi bond opened up, you have 6 valent electrons. So this will come back down to make the carbonyl. This falls off, you're gonna get that. Because if you make the carbonyl back, the carbonyl that is reformed should be this part right here in red. Okay, so this is the red part, and that's the black part. So you're losing Cl and you're losing sodium. So this is wrong. The byproduct here is sodium chloride. The sodium counter ion and the Cl makes sodium chloride. So that's a correction on the notes. So we will continue with this reaction in the next lecture session. Reaction of anhydrides with ammonia.